So let's change the circuit and let's look at a different one which has the two light bulbs now not connected one after the other but side to side. We're going to say that these two light bulbs are connected in parallel, and we'll have to define that precisely. So what do we have? Here? So I have connected a voltmeter here. The batteries are still 9 and 9, so that's 18. This ammeter at the bottom is telling me what's the current that I have in this circuit with the two light bulbs connected. Let me get rid of one of those light bulbs and see what happens to the current. So before it was 3.6 amps when I had the two light bulbs. Now that I only have one light bulb, the current is 1.8 amps. Why did the current go down? Again, notice that removing the light bulb left the circuit open on this side. So the electrons cannot flow from one wire to the other because they will have to jump through the air, and the air is a pretty good insulator. So back to the question, why is the current now less than it was before? If you think about it, it's kind of strange because a light bulb is a resistor. So if you add another light bulb here, instead of one light bulb, now you have two, you would expect intuitively that the resistance of the circuit is bigger because you're adding resistance to the circuit, right? In a loose way of speaking, you're just adding more resistance to the circuit. So you would expect the current to go down, not to go up, right? So what's going on? How do we understand that? This is the same thing that we discussed when we talked about the resistance of when we had a battery and we connected a cable. Right? So we said there is an amount of current going through that cable, that one cable, which is equal to the voltage of the battery divided by the resistance of the cable. Right? But what if I connect now two cables? I add one more cable to this. We said that now each cable is drawing an amount of current equal to the voltage of the battery divided by R. So each cable has the same current now, and the total amount of current going out of the battery is 2 times I as opposed to 1I before. Right? So if you put that in terms of Ohm's law, you would see that that is equivalent to saying that the resistance of the circuit is going down. If that still sounds weird, think about it this way. 610 loop. So it's a circuit, right? And it has a number of lanes, say 5 lanes, whatever number it has. And the traffic, the flow of cars is going there and so on at a certain rate. And now you add another part right parallel to it with the same number of lanes. Would that help the flow of cars in the highway or not? It obviously helps. Even if you add one lane, you will get better flow in the highway. If I add a light bulb with a large resistance right next to the other light bulb, even if the resistance of that light bulb is a lot, that's still helping the flow of current in the circuit. You're providing an additional path for the electrons to take, so that makes their life easier. Not all of them have to, say, squeeze into a single path. Alright? So adding resistance in a circuit, you cannot say that it always increases the resistance. It depends on how you add the resistance to the circuit. If you add one more resistance in series with what was already there, then you are increasing the resistance of the circuit by adding resistance. But if you add a resistor in parallel with another one, you're dropping the net or the equivalent resistance of the circuit. Therefore, the current goes up. Okay? So adding a light bulb here would increase the current. From 1.8 to 3.6, I'm adding an identical light bulb. Notice that the current here. It's 3.6 here, as it is on this side, of course, we already talked about that. And that the current on this path will be 1.8. If the light bulbs are identical, there will be no preference for one path over the other. So 1.8 amps will go this way, and 1.8 amps will go the other way. If the resistors were different, then the currents would not have to be the same. Alright, so let's do the math for this circuit. and figure out what's the general equation for the resistance of the equivalent resistor. The resistor that would do the same job as the two resistors connected in parallel. So my circuit has the battery and one resistor here and the other one connected here. And let's talk about again point A, point B, point C, D, and E. If I move along this circuit, what are the differences in potential that I will measure? If I move from A to B, the difference in potential is going to be the EMF of the battery, right? So let's say that I'm going to move, I know the current is going that way, and I'm going to go this way, and I'm going to go across here, and I'm going to go back to the battery following that path. Now I have two possible paths. I can go through resistor 1, or I can go through resistor 2, right? So let's do the first one. If I go from A to B, my potential increases by epsilon. If I go from B to C, what happens to the potential? Nothing, it's an ideal cable, so that's a 0. When I go from C to E, what happens to the potential? Am I going downstream or am I going upstream when I go from C to E? You're going down, so that means that you're dropping in potential. So that's going to be a negative sign because your final potential is going to be lower than your initial potential. So that's going to be minus, I'm going to call that I1, and the current here, I'm going to have to call that I2, right? I should not make the mistake of assuming that I1, the current going through resistor 1, is the same as the current going through the battery. Because the current, when it gets to point C, has an option. So some of the current is going to go one way, some of the current is going to go the other way. I cannot say that I is equal to I1. So the drop in potential, as we just said, is I1 times R1. That's between C and E. When I go from E to A, nothing happens to the potential. That's an ideal cable. And I'm done. I'm back to A. So I finish this by saying that this is equal to 0. So from here I get that the current flowing through resistor 1 is equal to epsilon divided by R1. So the current flowing through resistor 1 only depends on resistor 1. That's pretty interesting. It doesn't matter whether you add, whether you have R2 or some more other resistors connected in parallel, because the current going through R1 is only dependent on the difference in potential between the two sides of the resistor. And that difference in potential is set by the battery to be epsilon. The battery is making sure that that is epsilon, right? Batteries are sources of potential difference. They make sure that the potential difference for the parts of the circuit that are connected to them have the same as the potential difference between the battery terminals. If we do the same exercise, now we can go from A to B, B to D, that whole trip from B to D, then back to E and back to the battery. So if we do that, then we're still going from A to B, we're getting epsilon, B to D, that's 0. Now when we go from D to E, we are going downstream. That means the height must be dropping. So therefore I go with the minus sign, and the current flowing in that resistor is R2, and I multiply by the resistance 2. Between E and A there is no difference in potential, so I add a 0 there. And since I'm back to A, this sum should be equal to 0. So therefore from that equation I get that the current number 2 is this. And once again, it doesn't depend on whether you put R1 there or not. So if I know the EMF of the battery and I know the resistors, I know each one of the currents going through those resistors. One thing that I haven't figured out yet is what is the total current then? What is the current going through the battery? So for that we use Kirchhoff's junction law. It says that every time you have cables that are coming together at one single point, the sum of the currents at that point should be equal to 0. The currents that are coming in, you can call those positive. The currents that are coming out, you can call those negative. If you add all of the currents in a loop, that are coming in or out of a node, conservation of charge tells you that if this is I1 and this is I2 and this is I3, conservation of charge tells you that when you add those currents with their proper sign, I1 plus I2, let's say that incoming are positive, outgoing are negative, should be equal to 0. The incoming currents should be equal to the outgoing currents. So since I1 in this situation that I sketch here, since I1 and I2 are coming in, the sum of them should be equal to what's coming out, which is I3. Otherwise, charge will be lost in the process. So I3 should be equal to I1 plus I2. Okay? So if we use that idea, then the net current in the circuit, which is the current flowing here and across the battery, if you look at this point, for example, that point, that junction has the total current I coming out of it, and that junction has two currents coming in. This is I1 and this one is I2. So the final calculation then tells us that the current in the circuit, so the final calculation says that the current is going to be equal to I1 plus I2, and we just calculated how much each one of those is. So we have epsilon divided by R1 plus epsilon divided by R2. So now we know the net current flowing in the circuit. Same question as before. What would be the value of the equivalent resistance that would do the same job as these two resistors connected in parallel? So one circuit that we have has two resistors, and we want to simplify this circuit. We want to get rid of one of those resistors so that we get the same current for the same amount of voltage. Now I want to make a simplified version of this circuit that only includes one resistor. So I want to have the same current given the same epsilon. Now the current in that circuit is clearly going to be just epsilon divided by the equivalent resistance. And I want this thing to be equal to the current that I have in the circuit with two resistors. So that's epsilon divided by R1 plus epsilon divided by R2. So this equation, it's telling me how much is the equivalent resistance. You have epsilon everywhere, so you can turn it into 1, divide everywhere by epsilon, right? And the equation that you have for the resistance of the equivalent resistor is this. So you're adding the inverse of the resistors instead of just adding the resistors directly, right? In series, we said the equivalent resistance is R1 plus R2. In parallel, we're going to say the inverse of the equivalent resistance is equal to the sum of 1 over R1 plus 1 over R2. So now it's time to pay attention to what it means to be in parallel. So what can we say, what it would be the definition of something in parallel? So here's how we can define that. This is one resistor over here. To be in parallel, there has to be a conductor, continuous piece of conductor. That would take you, if you started from one side of the resistor, that would take you without interruptions to the other side of the other element, the other resistor that you have. You're considering whether A and B are in parallel. So start from B or A, doesn't matter. Start moving along a cable. If you can go continuously without interruption, without having to go through another resistor, right? Continuous cable that takes you from one to the other on one side. And you can do the same thing on the other side. Those two resistors are in parallel. Now don't be fooled by the fact that you're sort of recording in your mind the information, the visual information, that a lot of times we draw resistors in parallel as being physically or geometrically in parallel with each other. That's supposed to make things a little clear, but then people get stuck with that image, and whenever they see that two resistors are geometrically aligned, they want to throw in a parallel resistors equation, and that's not what you want to do all the time, right? So the condition, you have to make sure that you can go from one side to the other uninterruptedly following an ideal conductor. So you might have two resistors that look like this, right? But what if this is the connection that they have? Clearly they're not in parallel just because they look like they are in parallel. If I go from one side here, can I reach the other side of the other resistor moving through a cable without any interruptions? The answer is no. The only possibility I have is to go this way, and when I go this way I'm going to have to go through a battery, and that doesn't count. That is not good, right? It has to be a continuous wire taking you from one side to the other. You can say that at the bottom you do have a continuous cable, but it has to be on both sides, not just one side. On this side that condition is satisfied, but on this side that condition is not satisfied.
What about a junction like in between? If the cable goes off somewhere else, so there is a connection?
Where?
So if you put a junction like up here that goes off to something,
they would still be in parallel. Yeah, that's an important question. If you had a cable connected here, that doesn't change the fact that you can still move continuously from one side to the other following a cable. They're still in parallel.